Hello, my name is Chris Johnson, and this is my video report for Lab 1, Constant Velocity for Physics 2211. In this report, I will introduce the problem alongside the observation video, explain how I used Tracker to collect and visualize data from the video, then explain how I built a computational model through GlowScript to predict the object's movement, and finally I will compare the observed results to the predicted results and evaluate the performance of my computational model, citing any possible improvements that could have been made at the end. In this lab, I'm building a model to predict the movement of this basketball with a constant velocity. If we can accurately do this using a computational model, we can apply this to any objects in the real world which move at a constant velocity to predict their future movement, as well as lay the foundation for more advanced future models. To set up Tracker, I first had to choose a start and end frame. I chose this frame which is well removed from initial contact, and this final frame which occurs before the ball begins to change direction. I took note of both frame positions. Next, I needed to create a size reference so Tracker can accurately calculate distance throughout the video. A men's basketball is 9.55 inches in diameter, which converts to 0.243 meters. I also needed to point out the center of mass of the system in order for Tracker to accurately identify distance covered. Now that everything is referenced, I can begin going frame by frame identifying the updated center of mass. As I input this, Tracker is tracking the time and position of the ball on the right side of the screen. With no nonsensical data and a pretty constant slope, I'm satisfied with the collected data. The x position is increasing in the negative direction because I'm using a standardized axis, denoting left as negative. If I were to invert these axes and made left x positive, the graph would have the same slope but be mirrored across the x-axis, being placed in quadrant 1. I'm going to need some data from Tracker on the right side of the screen to help build my computational model. We'll go into more detail on the formulas later, but we know that the position and velocity update formulas need a time interval and an initial velocity. Using the data from Tracker, I listed both the initial and second positions of the ball. I subtracted the initial from the final, dividing by the frame rate of Tracker, which is 0.033 seconds. That gave me an initial velocity of negative 0.8697 meters per second. The time of the last observation was at 1.101 seconds. Now that we have all the necessary data, we can build our computational model in GlowScript. The link to the code is in the description of this video. The first initializations I make are the mass of the basketball in kilograms, as well as the ball's initial position and velocity, which we collected from Tracker. Delta T is 0.01 seconds, which is about 1/100th of our observation video, which provides us plenty of data points. In terms of the physics formulas, which our prediction will be based around, let's look at lines 60 and 62 in more depth before explaining line 56 and the while loop as a whole. This is our velocity update formula in code form. It's taking the initial velocity we provided and assigned from Tracker, adding it to the change in velocity, and creating a new assignment for velocity every loop, or every 0.01 seconds. In terms of our position update formula, which is the driving factor in our prediction, it takes the initial position we provided and assigned from Tracker, adds the change in position by multiplying the ball's velocity by the change in time, and creates a new assignment for every loop, or for every 0.01 second. Going back to the velocity code, it's important to remember that we are trying to predict the movement of an object with a constant velocity. It is impossible for the velocity to be constant if there's a constant force being added to it. That would result in acceleration. So to make the whole change in velocity section 0, we must make our F-net vector equal to 0 in line 56. It is possible to measure the forces acting on our system which make the net force 0. If net force is 0 and friction is considered negligible, the two equal and opposite forces on the ball are the gravitational force and the normal force from the table. Now that all our formulas are ready, we place all of this in a while loop, which will execute every delta t, which is 0.01 seconds. The loop will repeat until our observation time expires at 1.101 seconds. Let's run the code. I see two similar graphs, which make sense and seem to be very similar, so I'm satisfied and ready to compare and visualize. I move all information into Excel and then clean up the graph. Immediately, I see that there is a quite noticeable difference in the predicted data versus the observed. Although initial velocity was the same, the observed velocity slows down from where it began. This can be attributed to two things. Velocity was not constant and deceleration was present, or the initial velocity was recorded too close to my hand's initial contact with the ball while the ball was still accelerating. After reviewing the footage, I can deduce that I should have allowed more time for the ball to accelerate when picking the frame of the first video. For final critique, I should have allowed more time for the ball to initially accelerate to record a more accurate initial velocity. This could have been easier if I used a larger setup so I could have more time and space to choose the best beginning and end frames. Thank you for watching my lab report on Lab 1, Constant Velocity. Please see the description for the link to my GlowScript code.